another episode of Sci-Connect. I am Teacher Nell, your science teacher for today. Are you now ready to learn? Let's start! Hello grade 9 science learners! Welcome to our new video lesson for today, which is all about electronic structure of matter. The most essential learning competency for this lesson is to explain how the quantum mechanical model of the atom describes the energies and positions of the electrons. The specific learning objectives are the following: relate the colors emitted by elements to the structure of the atom, write the electron configuration of the elements in the third period, cite the economic importance of elements attributed by its electronic structure, and to determine how much you learn about electronic structure of matter in your grade 8 and grade 9, let's have a pre-assessment. Try to answer the next 5 questions. Direction: identify what is asked or described in each item, then write the letter of the correct answer in your notebook. Number 1. If the first and second energy levels of an atom are full, then what would be the total number of the electrons in the atom? A 6, B 8, C 10, D 18. Number 2. Which electron transition results in the emission of energy in the flame test? A 3p to 3s, B 3p to 4p, C 2s to 2p, D 1s to 2s. Number 3. Which of the following sublevels is correctly designated? A 1p5, B 3f9, C 2p6, D 3d11. Number 4. Which configuration is possible in an excited state of electron? A 2 each helium is equal to 1s2, B 1 hydrogen is equal to 1d1, C 11 sodium is equal to 1s2, 2s2, 2p6, 3d1. Letter D, 10 neon is equal to 1s2, 2s2, 2p5, 3s1. Number 5. What are the orbitals present in the fifth principal energy level? A s orbital, B sp orbitals, C s, p, and d orbitals, D s, p, d, and f orbitals. The spectacular fireworks that you have observed or you have witnessed is from Pyro World in France. So, what's the science behind it? As early as the 17th century, knowledge about the structure of the atom grew when scientists began to study the emission and absorption of light from different elements. As you watch the next video, you will find out what happens when metals are subjected to heat. The colors you will observe could be related to the structure of the atom. What to do? Number 1, watch the video experiment on the next slide. Number 2, answer the guide questions that follow.
You may want to go back and look at the calcium one, compare that to the strontium one. This is barium. Here's to give off the yellow-green color. Now it's gone. So as soon as you touch your substance into the flame, that's the color that you're observing. The longer you hold it in there, the longer the chance that it's going to burn off. So that initial color that you first witnessed when you put your substance into the flame is what you should be observing. So it gives the yellow-green color. The last substance is copper. See, this puts off a blue bright blue-green color. Different than the barium. The barium was more yellow-green, whereas this is that bright blue right in the center and green highlights on the outside. I'm not really sure what the yellow is jetting off of that. That typically does not happen. So you should be looking at that blue and green is copper.
Guide questions. Why do you think are there different colors emitted? What particles in the heated compounds are responsible for the production of the colored light? How did the scientists explain the relationship between the colors observed and the structure of the atom? The electrons are moving around the nucleus in circular orbits. When an electron absorbs extra energy from the flame, it moves to a higher orbit. Colored light is emitted when the electron falls back to a lower orbit. This light is a difference between the energies of the two orbits involved. The quantum mechanical model views an electron as a cloud of negative charge having a certain geometrical shape. This model shows how likely an electron could be found in various locations around the nucleus. The volume or region of space around the nucleus where the electron is most likely to be found is called the atomic orbital. The quantum mechanical model also gives information about the energy of the electron. The model also describes the region of space around the nucleus consisting of shells. These shells are also called principal or main energy levels. These principal energy levels or shells may have one or more sublevels. These sublevels are assigned with letters S, P, D, F, and G as shown in the next slide. We have the principal energy level or N, 1, 2, 3, 4, and 5. Number of sublevels, we have 1, 2, 3, 4, and 5. Type of sublevel and number of orbitals, we have for 1, S or 1 orbital, 2S, 1 orbital or 2P, 3 orbitals, 3S, 1 orbital, 3P, 3 orbitals, 3D, 5 orbitals, 4S, 1 orbital, 4P, 3 orbitals, 4D, 5 orbitals, and 4F, we have 7 orbitals. For 5S, we have 1 orbital, 5P, 3 orbitals, 5D, 5 orbitals, 5F, 7 orbitals, and 5G, 9 orbitals. The maximum number of electrons can hold for a principal energy level 1, we have 2. For principal energy level 2, we have 8. For principal energy level 3, we have 18. And for principal energy level 4, we have 32. And we have for principal energy level 5, we have 50. As shown in the table 1, the principal quantum number is always equal to the number of sublevels within that principal energy train. The maximum number of electrons that can occupy a principal energy level is given the formula 2 sub n or 2n superscript 2, wherein n is a principal quantum number. Guide questions. Based on the table 1, how many types of orbitals are in principal energy level 3? Number 5, using the formula 2n2, what is the maximum number of electrons that can occupy a principal energy level of 4? For number 6, how many atomic orbitals are in the highest sublevels of principal energy level 3? In an atom, electrons and the nucleus interact to make the most stable arrangement possible. The way in which electrons are distributed in the different orbitals around the nucleus of an atom is called the electron configuration.
Sublevel has 1 orbital, PS3 orbitals, DS5 orbitals, and F has 7 the electrons occupy. Now, the electrons fill the orbitals according to a pattern. So here's the question. We've got all these different energy levels. We have different sublevels. S, SP, SPD, SPD, and F. And then within these sublevels, we have all these different orbitals. The S has the 1 orbital here, the P has the 3 here, and the D has the 5. So where would the electrons go if you were to add one at a time? Would it go to this energy level, or this energy level, or this energy level? If the electron went to this energy level, what sublevel would it go to? And if it went to a certain sublevel, let's say it went to the P sublevel, would the electrons, go here, or would they go here? So we have to figure out where in all this mess the electrons would go. And the distribution of electrons follows a pattern. Now we're going to use a diagram to find the pattern. And first we need to use the chart below. Now, this is a chart that you saw in the previous lecture, so you should have this memorized. The only addition we've added is that in the 5th energy level, there's S, P, D, F, and I think G comes after F, but usually you don't go any further than F. So just remember that these are the sublevels inside each of the energy levels. And we could take this out to 6, 7, and 8 and just keep writing S, P, D, F, but we only need to go up to 5. All right, so what we're going to do is I'm going to draw a diagram based on this information right here. So this just shows the energy levels and the sublevels that are in each energy level. So the first energy level has an S, the second has an S and a P, the third energy level has S, P, and D, fourth has S, P, D, and F, and then after that, all the rest we just write S, P, D, and F. So fifth has S, P, D, and F. All right, so here's what we're going to do. I'm going to start drawing arrows through each of these terms. And the arrow is going to start from the top left and go down, top right and go down to the bottom left. And we sort of slice the arrows through. Each time we draw an arrow, it has to slice through first term of the next horizontal row. Anyway, so the first arrow goes through like that. The next arrow I draw has to go through the first term of the next row. So the next row is this row right here. There's the first term. So arrow goes like that. Here's the first term of the next row. So the next arrow has to go through like that and hit that one. Here's the first term of the next row. The next one goes through here. Here's the first term of the next row. So the next arrow goes through here. Now it's possible I could have written a row 6 and a 7 and keep drawing that pattern, but we only need to go up to 5. All right, now look at the order in which we draw the arrows. The first arrow goes through 1S. So I'm gonna write 1S. The next arrow goes through 2S. I'm gonna write 2S. The next arrow goes through 2P and 3S, and that's what I'm gonna write in that order. I'm gonna write 2P first, then 3S. 2P, then 3S. The next arrow goes through 3P and 4S. So I'm going to write 3P, and then 4S. And then the next arrow goes through 3D, 4P, 5S. 3D, 4P, 5S. Okay. These are written out in the order in which the arrows slice through them. All right. The next thing we need to do is I'm going to draw horizontal lines over the top of each of these terms. The number of lines I draw depends on the sublevel. S has 1 orbital. P has 3 orbitals. D has 5 orbitals. F. Oh, we didn't go as far as F. Well, yeah. So we don't. It has 7. We won't need to use it. This was in the previous lecture. You need to memorize this. Okay. So 1S. S has 1 orbital. I'm going to draw a single line above it like that. 2S. Once again, S has 1. 2P. P has 3 orbitals, so I'm going to draw 3 horizontal lines over it. S has 1. 3p, p has 3. 2, 3. 4s, s has 1. 3d, d has 5, so we're going to draw 5 lines above the 3d. 1, 2, 3, 4, and 5. 4p, p has 3 on top. 1, 2, 3, and 5s, s has 1. That's it. So this configuration here is this little diagram is what we're going to use to figure out where to put the electrons.
Sa ba sa mga aero eh? Ano man na? Na-record ang ilang boses.
You're getting further and further away from the nucleus.
Magbalik na po ko sa zero.
Increases as you go from left to right.
Kapila ko nag-balik.
Right here.
Kalima na aka na pulo na
You want to get close to the nucleus, so they're going to fill in these little slots from left to right. Draw my S here because font and unseeable. We're only going to go up to a 4p. So you go from left to right, energy increases. Basically, it means when we say energy increases, it means getting further and further away from the nucleus. You need to memorize this diagram or memorize the procedure for making this diagram. All right, now. Next thing we're going to do is draw arrows on the horizontal line to indicate that an electron's in an orbit. And in general, we're going to fill the lines from left to right. And electrons want to get close to the nucleus, so the left side gets filled in first. So when we fill in this diagram, we're going to start on this side. We're going to go across. Okay. And when you fill in the diagram from left to right, that's also known as the Aufbau principle. And it just means that electrons fill the lower energy levels first before filling the higher energy levels. So that's just a fancy way of saying we fill in the diagram from left to right. So here are the rules we're going to use for filling in the orbital diagram. All right, so first you choose the lowest energy level. That means you're going to start as far left as you can. Choose the lowest sublevel, S, P, D, or F. Once again, it just means we're going to go from left to right. Fill the orbital with a maximum of 2 electrons and have them spin in opposite directions. I'll draw you a picture. I'll show you what that means in a bit. And before a second electron can be placed in any orbital, all the orbitals of that sublevel must contain at least 1 electron and spin in the same direction. That's a lot of words, and we'll show you what rule number 4 means when we actually draw the diagram. Right now, it probably doesn't mean much. It'll have meaning when you see it actually done. Okay, so to do this, you need to use a periodic chart to get the atomic number. Remember, the atomic number tells you the number of electrons the atom has. All right, so hydrogen has 1 electron. Where does the electron go in this whole mess? Well, we start from left to right. The first electron goes here, the leftmost. We're going to draw an arrow to indicate that it's an electron. So the arrow represents an electron, and that's the electron spinning in one direction. Okay, that's pretty straightforward. That's the electron configuration of a hydrogen. Let's do the next element. Draw the electron configuration for helium. 2 electrons. 1, 2. And notice I put 2 arrows on here. Why? Because each line or each orbital can hold a maximum of 2 electrons. Notice also that 1 arrow is up and 1 arrow is down. When 2 electrons occupy the same orbital, they have to spin in opposite directions. That's the Pauli exclusion principle. Let's draw the electron configuration for the next element. Lithium, 3 electrons. Here we go. 1, 2, 3. And we have to put the 3rd electron here, because this one already has 2 in it. Can't hold any more than 2, so we run out of space here. Go to the next one over. Let's draw the electron configuration of beryllium. 4 electrons. 1, 2, 3, 4. Okay? 2 electrons on that one, spinning in opposite directions. Let's draw the electron configuration for boron. 1, 2, 3, 4, 5. Okay, so we're just going from left to right. We're putting 2 arrows in each one, and the arrows are spinning in opposite directions. All right, now we're going to do one. It's going to deviate from the pattern a little bit. I'm going to throw you a little bit of a curveball. Draw the electron configuration for carbon. 6. 1, 2, 3, 4, 5, 6. That's where you place the 6th electron. Now, why didn't I place this electron on this line upside down? It's because of rule number 4. Rule number 4 says that before you can put a 2nd electron on this one, all these other ones have to have at least 1 arrow in them. All right, so I can't put a 2nd electron in this one until all the rest of these also have 1 electron. And when you put them in, they have to be facing in the same direction. Let's do nitrogen. I think you can continue to see the pattern. 7 for nitrogen. 1, 2, 3, 4, 5, 6, 7. Once again, why didn't I put this one in either this one or this one? And before either one of these lines can have a 2nd electron in it, all the rest of the lines have to have 1 arrow on them. Okay, let's do oxygen. 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Now I can start putting a 2nd electron in this one because these other ones now have 1 electron in them. Right? So I can't put 2nd electrons on here until all the rest of these have at least 1 in there, and they do. So that's why I was able to take the 8th electron and put it right there. Let's do chlorine. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I was able to put the 2nd electron here because all these other ones had at least 1 electron. Let's do 10 electrons. 1, 2, 3, 4, 5, 6, 7, 9, 10. Okay, so I was able to put the last electron here because all these other ones had at least 1 electron in them. All right. Let's do it for vanadium, atomic number 23. You ready? So you should be able to do this since you've seen the pattern. 23, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and 23. And then the 24th and 25th would go here and here. So 23, 24, 25, and then the 26th would go here. And then you would fill it up here, and then you would start doing these. Okay? So before you can put 2nd arrows in it.
Try to do the next activity. Write the electron configuration of the elements in the 3rd period of the periodic table. The elements are sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Write your answer in your notebook or in your answer sheet. Excited state of electron. When an electron of an element such as neon absorbs extra energy from the flame or electric arc, this electron moves to a higher energy level as shown in the electron configuration below. Neon 1s2, 2s1, 2p5, and 3s1. At this point, the electron is at its excited state. The same electron can return to any of the lower energy levels, releasing energy in the form of light with a particular color. Guide questions number 7. What are the patterns that you have observed in the distribution of the electrons? Answer this. What is the scientific explanation behind the spectacular colors of fireworks display? Task. Choose 3 objects in the box below, then cite its economic importance attributed by their electronic structure. Write your answer in your notebook or your answer sheet. Don't forget to submit your answer to your science teacher. This time, let us answer the post-tests. Direction. Identify what is asked or described in each item. Then write the letters of the correct answer in your notebook or in your answer sheet. Number 1. Which orbital designation has the highest energy? A 2s, B 2p, C 3d, D 4s. Number 2. Which of the following sublevels is correctly designated? A 1p5, 3 B 3p9, C 2p6, D 3d11. Number 3. How many orbitals are in the third principal energy level? A 3, B 6, C 9, D 2, and 4. Which electron transition results in the emission of energy in the flame tests? A 3p to 3s, B 3p to 4p, C 2s to 2p, D 1s to 2s. Number 5. Which configuration is possible in an excited state of electron? A 2 helium is equal to 1s2, B 1 hydrogen is equal to 1d1, C 11 sodium is 1s2, 2s2, 2p6, 3d1. Letter D, neon 10, 1s2, 2s2, 2p5, and 3s1. Part 2. Direction. Shown here are the orbital configurations for the elements named. Each configuration is incorrect in some way. Identify the error in each and write the correct configuration. 1 carbon, 2 calcium, 3 chlorine, 4 aluminum, 5 titanium. Try to look and take your time to answer the question. Congratulations, learners, for finishing the visual lesson. I hope you enjoyed learning with me today. Remember, learning is fun with Sci-Connect.